All right, so let's kind of put all of this stuff together. We've talked a lot about the intermolecular forces. We've talked about the intramolecular forces. We've talked about physical properties, comparing ionics and covalents and then metallics. So how does this all fit together? How do the intermolecular forces really affect those physical properties? So let's take a look first at solids, liquids, and gases. So like we talked about at the beginning here, solids, we know, have really tightly packed particles. They're very ordered structure to them. You have all of these interactions between those nearby atoms or molecules or ions or whatever it is, causing very little movement. In order to have a solid state of matter, you have to have a really strong intermolecular or intramolecular force holding those things together. Liquids have a little bit more wiggle room because there's more movement. They're able to slip and slide past each other. There are still somewhat strong intermolecular forces holding those together to nearby molecules, but it's just not as strong as you would see in a solid. And gases have really weak or non-existent intermolecular forces between the particles. Ideally, you wouldn't see any kind of attractive force between them. Real gases, though, we'll talk about those. Anyways, so when you're comparing solids, liquids, and gases, and trying to tie in the inter and intramolecular forces, your strongest IMFs would typically form a solid state of matter. Your weakest IMFs are typically going to form gases. Melting point and boiling point. We've already talked a little bit about this during that metallic bonding. Melting point, as we know, that's going from a solid to a liquid. Boiling point, we know, is going from a liquid to a gas. So in both of those cases, solid to liquid or liquid to gas, you're going from a stronger intermolecular force to a weaker intermolecular force. So you have to put energy in order to weaken those intermolecular forces and get the particles to separate to form that other state of matter. So the stronger the IMF, the stronger that attractive force between the particles, the more energy it requires to pull those things away from each other. So substances that have really strong inter or intramolecular forces would have really high melting points and boiling points. That's why we saw during the ionic and covalent properties lab that those ionic compounds typically had a high melting point because ionics, like we've talked about, are the strongest intermolecular force. Since they're the strongest, it takes more energy to pull those ions away from each other. We talked about how covalents, they're more volatile. They escape into the gas form more easily. Or we saw that they melted quicker than the ionic compounds did. And that's because they typically have the weakest intermolecular forces. They have those dipole-dipoles or those London dispersion forces, making it a little bit easier to melt or to boil. So let's take a look at this. Which have higher melting points? Ionic compounds or covalent molecules? We know that the higher ones are going to be ionic. Which bond is stronger, ionic or covalent? Ionic is, that should not say covalent, that should say ionic. Ionics are stronger. That's why they have the higher melting points and the higher boiling points. I will change this before I upload this into Schoology, okay? So ionic bonds are stronger. Would metals have higher or lower melting points than the covalent molecules? They're going to have a higher melting point or a higher boiling point because the metallic bond is stronger than those covalent intermolecular forces, okay? So next, we want to arrange these substances in order of increasing boiling point. So again, you need to figure out what kind of inter or intramolecular force is holding these samples together, because that's what you're going to use to compare the boiling points. So there's layers of thinking. If it's covalent, you might have to draw this. So first off, we can see that copper, we know, is held together by metallic bonds. So this is metallic. I need to compare all of these inter and intramolecular forces first. H2, that's a diatomic molecule. I know that's just going to be LDF. H2O, I can look at that and see that that's going to be held together by hydrogen bonds. LiCl is ionic because it has a middle and a non-middle. And H2S, if I were to draw this out, I would see that the sulfur is in the middle and it has lone pairs on that sulfur, and it would be dipole-dipole. Now I can arrange these in increasing boiling point. So remember, the weaker the IMF, the less energy it takes to boil, and so the lower the boiling point. So which of these has the weakest IMF? H2 is the weakest because it only has those London dispersion forces. What's the next weakest? The H2S, because it's dipole-dipole. What would you expect to have the next highest boiling point? The H2O, because it has hydrogen bond. All three of these things are covalents, and they tend to be weaker, thus having the lower melting points and the lower boiling points than metals and ionic compounds. Now we're left with the Cu and the LiCl. The copper, because it's metallic, is going to have slightly lower melting and boiling point than you'd see with that ionic compound. Okay, ionics are going to tend to have the highest melting points and the highest boiling points. Which of the following is expected to have the highest normal boiling point and why? Well, when I look at these, C2H6, C3H8, C5H12, C4H10, all of these are hydrocarbons. It's a carbon-hydrogen chain. They're all London dispersion forces. So if I think way back to when we talked about London dispersion forces, I have to remember how to determine which LDFs are weaker and which LDFs are stronger. So the more electrons there are, the longer the chain, the more polarizable it is. So these really compact ones over here, such as the C2H6, I know those are going to have a lower LDF, and that means it's going to have a lower boiling point. The longer chains, there's more mass, more electrons, more polarizable. It's going to have a stronger LDF, so it would have a higher boiling point. So my answer should be letter C. And number 2, which of the following is expected to have the highest normal boiling point and why? I can look at all of these. What do I notice in all of these? They all have hydrogen. Are any of these hydrogen bonds? Because hydrogen bonds would be higher than a dipole-dipole interaction. In a hydrogen bond, you would expect to see stronger IMF and thus a higher boiling point. So HF would have the strongest IMF, which would have a higher boiling point. The last thing we want to talk about is vapor pressure. So vapor pressure is a different physical property. Vapor is talking about the ability to go from liquid to gas. So when we have a closed container, you've got molecules that are in the liquid phase down here that just escape into gas form when they get close to the surface, and that attractive force is weak enough for it to escape into a gas. When it escapes into a gas, it hits the sides of the container, creating a vapor pressure. The more times it hits the container, the higher the vapor pressure. The less times it hits the container, the lower the vapor pressure. So we're trying to figure out which types of substances would have a higher vapor pressure. Well, those would be the ones that's easiest to escape into a gas form. So lower, weaker IMFs. If it has a weak IMF, it's going to have a high vapor pressure, because if these IMFs are weak, it's going to be able to escape into the gas form easily, hitting the sides of the particles more frequently, increasing the vapor pressure. If it has a stronger IMF, that means that it's going to hang on to those particles more. The attraction is going to be stronger. There's going to be less things escaping into the gas form. We're going to have a lower vapor pressure. Okay? If you have any questions about vapor pressure or physical properties of any kind, comparing all of these different IMFs, let me know. I'm here to help. Just a reminder, if you're in doubt, if you're looking at these problems and you can't think about what to do, start by asking yourself the big picture question. Is this ionic? Is it covalent? Is it metallic? If it's covalent, You have to ask yourself a sub-question. Is it polar or non-polar? You might have to draw it so that you can see, is this going to be a polar molecule or a non-polar molecule? Because if it's a covalent molecule, you have to figure out which kind of intermolecular force is involved. Is it hydrogen bond? Is it dipole-dipole? Is it London dispersion force? Okay? Hit me up if you guys have any questions at all. Thanks.